So we're covering chapter 8.3. 8.4 is a single selection. In chapter 8.3, we'll be looking at hypothesis tests in detail. And by that, I mean we're not going into an extreme amount of detail, but just enough to gain an understanding of the topic. And we were also going to look at identifying two possible sources of error in hypothesis testing. Now, let's revisit small p-values. Big deal here. A small p-value means that our test statistics, the z, is extreme. In other words, it is very far to the left or to the right of the zero. Okay? Understand what that means in terms of the zero. If the zero is in the middle, the smaller the p-value is, the further away we are from zero, the more extreme that number is, the smaller the p-value would be. Okay. Now, an extreme test statistic means something unusual and therefore something unexpected has happened. And remember that small p-values that are generally less than 0.05 reject the null hypothesis. Okay, so this is just what we know already. Now, let us look at conditions fail. If the conditions concerning the sampling distribution of a z-statistic fail to be met, then we cannot find a p-value using the normal curve. Conditions can fail for two reasons. Actually, more than two reasons, but we'll discuss a couple in a. One is that the sample size is too small, and then that the samples are not randomly selected. In this case, conclusions may not generalize the entire population. For example, if you're trying to take a survey on, say, women who are pro-life, and you don't select your sample randomly, you just select women who are pro-life, then of course your conclusions may not generalize the entire population, and your results are going to be inaccurate. So, potential mistakes in hypothesis testing. There are two types of potential mistakes that can occur in hypothesis testing. Okay, firstly, if the null hypothesis is true, bad. The probability of doing this is called the significance level. Fail to reject the null hypothesis, good. If the null hypothesis is false, good. Fail to reject the null hypothesis is bad. Now, why are these mistakes? So let's talk about why these could be potential mistakes. Suppose a political analyst is interested in predicting whether school bond measures on the ballot will pass. Her hypothesis test, the null hypothesis, P is equal to 0.5, an alternative hypothesis, P is greater than 0.5. Describe two types of errors she might make conducting this test. Okay, so we're going to describe the two types of errors that are mentioned here, and I'm using an example to kind of illustrate what's happening here, and then explain what a 5% significance level means in the context of this problem. So let's see what's happening, the mistakes that could be made. Rejecting a null hypothesis when it is true. This means that concluding that more than 50% favor the bond when the actual proportion who favor the bond is 50% or less. Okay? There could be one mistake that's happening. She went ahead and rejected the null hypothesis, even though the null hypothesis is true. Okay. And then, secondly, the second mistake is failing to reject the null hypothesis when it is false. This means concluding that 50% or less favor the bond when the actual proportion who favor the bond is more than 50%. So that kind of illustrates mistakes that could be made. Okay. If you, um, you know, reject the null hypothesis or fail to reject the null hypothesis uh, when um, when it is true or when it is false, you're making a mistake. The 5% significance level means there is only a 5% chance that the analyst concludes that more than 50% favor the bond when in fact they don't. Okay? So, again, the significance level is also affected by inaccurate conclusions. So, ways to reduce mistakes. The only way to reduce the probability of both types of mistakes is to increase the sample size. Increasing the sample size improves the precision of the test, so we make mistakes less often. Another way to reduce the mistake is we cannot make the significance level arbitrarily small, because this increases the probability that we mistakenly fail to reject the null hypothesis, right? In other words, 0.05 is a great level. If we go to 0.01, that increases the probability that we mistakenly fail to reject the null hypothesis. So, stick with the proven significance levels. 0.05 is great. Here are some cautions about writing conclusions. Because we can never be 100% certain that our conclusion in a hypothesis testing is true, when your p-value is greater than your significance level, avoid using any of the following phrases. We accept the null hypothesis. Don't say that. We have proved the null hypothesis is true. Don't say that. Okay? Instead, say we have failed to reject the null hypothesis, or we cannot reject the null hypothesis, because you've not proven that it's true. You're just failing to reject it or rejecting it. Most of our calculations for this section lie in chapter 8.4, how to conduct a hypothesis test from two populations, and I'm going to show you how to do that in the examples. Okay. Hypothesis one-sided and two-sided tests. Okay. Two-sided test, P1 is equal to P2 and P1 is not equal to P2. The populations are different in the proportions are different in the two populations. For a one-sided test, P1 is equal to P2 and P1 is less than P2. The proportion in 1 is less than the proportion in 2. And for one-sided right, P1 is equal to P2 as usual, and then P1 is greater than P2. Proportion in population 1 is greater than proportion in population 2. Okay, so these are the scenarios, because we're going to have to write those. For large samples, to check the conditions, you would add what's called the two proportions, x1 over n1 and x2 over x2, and make up p hat, the pool proportion, and then check to see that it's greater than 10 or greater than 10, 1 minus p, and so on. Okay, for both. Now, if we're told explicitly that the sample was randomly drawn, we may have to assume this condition is satisfied. Okay. Then independent samples. The samples are independent of each other, and independent within the samples. Observations within each sample must be independent of one another. I put the instructions with both StatCrunch and the calculator here, and I'm going to show you while we're doing the examples how to do those, okay? And finally, you will use the interpretation. Remember, if our p-value is small, less than our significance level, we reject the null hypothesis. We can conclude that consumer confidence has increased in whatever example we're talking about there. All right, now we're going to head straight to the problems. I want to make sure that you can answer these questions. They're, a little scary, a little different. A researcher carried out a hypothesis test using a two-tailed alternative test. Which of the following z-scores is associated with the smallest p-value? So if we go back to our notes and recall that uh, what we were told in the notes here, a small p-value means your test statistic is extreme. So let's go back to this problem. And we're trying to find which of the z-scores is most extreme. You have negative 0.49, negative 1.46, negative 0.209, and negative 0.342. That is the most extreme from 0. Okay? If we're going to the left or to the right of the number line, negative 3.42 is the furthest from the number line. So that z-score will have the smallest p-value. And we know that the z-score farthest from 0 has the smallest tail area and thus the smallest p-value. Make sense? All right. A test conducted in which a coin is flipped 30 times to test whether the coin is unbiased. The null hypothesis is that the coin is fair. The alternative hypothesis is that the coin is not fair. One of the accompanying figures represents the p-value after getting 16 out of 30 flips, and the other represents the p-value after getting 18 out of 30 flips. So which is which? Which one of the graphs here represents the one that is 16 out of 30 and which represents 18 out of 30? So the smaller if we looked at these proportions in terms of numbers, this is 16 divided 30 is approximately 0.53, and 18 divided 30 is 0.6. So clearly the second proportion is larger. Okay? In other words, this graph here, the first graph represents 16 out of 30 heads, and the second graph represents 18 out of 30 heads. Since 18 out of 30 heads, it's farther away from, you can see where the tails are farther away, so farther from half. It results in a z-value that is further from 0. And a smaller p-value. Okay? That 18 out of 30 will be further away from 0 and result in a smaller p-value because it's larger. It's a larger proportion. Makes a little bit of sense? All right. Now, is it acceptable? Question 3, is it acceptable practice to look at your research results, note the direction of the difference, and then make the alternative hypothesis test one-sided in order to achieve a significant result? No, no, it's not acceptable. You're cheating when you do that. You can't change the conditions. You can't change the alternative hypothesis to get the result you want. Changing the alternative hypothesis is definitely, uh, rigging the results, cheating. Okay, don't. If you do not reject the null hypothesis, is it valid that we accept the null hypothesis? Why or why not? Let me read this question again. If we do not reject the null hypothesis, is it valid to say we accept the null hypothesis? Oh, okay. So we're not saying. Remember again, going back to our conditions. I want to refer back to where we talked about this. Okay, right here, where we said we don't use accept or proved. Instead, we use fail to reject or cannot reject. So again, no, we have only shown here we do not reject the null hypothesis. We do not use accept. Instead, we say that we have not shown. So no, one of the answers be B and D. No, nothing to do with the second sample here. No, we have only shown that we do not have enough evidence to reject it, right? We want to keep rejecting in there. We don't want to put accept in there because we haven't proven anything. Just to draw a conclusion. Which of the following phrases should not be used when writing a conclusion, a hypothesis test? So think. You never use the word accept. Always say reject or fail to reject. So uh, don't ever say it's accepted to be true. That's not an acceptable. That's not an acceptable answer. Question 6. When comparing two sample proportions with two-sided alternative hypothesis tests, all factors being equal, will you get a smaller p-value with a larger sample size or a smaller sample size? So we discussed this already. The p-value will be smaller with a larger sample size. Okay, we discussed this in our notes. The p-value will be smaller with a larger sample size because a larger sample size results in smaller standard error, which is the denominator of the test statistic. All right, now we're going to look at some of the problems. Question 7 is in reality asking us to look at a problem here. They're not asking you to do the computation yet. They did the computation here. They're asking us to answer certain parts of this. Researchers reported on a study of patients with recurring chronic lymphatic leukemia, CLL. The study was randomized, double-blind, and placebo-controlled. After 12 months, so all of those conditions are met, right? Double-blind, independent of each other. In other words, randomized and controlled with a placebo. After 12 months, 106 of the 113 patients assigned to the combination treatment of IDEL with rituximab RIT were still alive, and 94 out of the 113 assigned a placebo with RIT were still alive. Perform a hypothesis test to decide to test whether those who take IDEL have a better chance of surviving than those who take the placebo. Use a significance level of 0.05. Can the researchers conclude that IDEL causes an increased chance of survival? So the first part will be the null hypothesis. The null hypothesis always has an equal sign, right? So in this case, P IDEL must be equal to P placebo. P placebo for the null hypothesis. They gave us the alternative hypothesis already, yes? In the second one, this is the alternative hypothesis here. The significance level of is 0.05. Choose the two proportion z-test. Although the sample isn't random, there are random assignments to the two independent groups. The pool proportion, so in the first case we have 94, we have 106 out of 113, and in the second case we have 94 out of 113. That pool proportion, we add the numerators, add the denominators, and get the pool proportion, and then put it into our calculator to get 0.8850. Okay, now this is where it gets interesting. Okay, so to test large sample, n1 times p hat, we've computed p hat here as 0.88, 0.8850. To calculate for large sample, we take the sample size 113 times p hat and we get 100 plus. Then we take the sample size, this is for the first sample, 1 minus p hat, and we get 13. Now we have to do the same for the second sample size, but because we're multiplying by the same 113, the numbers are going to remain exactly the same for this sample. Okay, this is going to be the same as N1, N2, and N1 are the same. They're both 113, and N1 and N2 are the same. So we're essentially multiplying by the same number for both. Okay. You don't have to actually do any work here and redo that calculation. You're done. Okay. Now, they gave us the printout of the technology here. The z-score is right here. This z-score, the 2 decimal places is 2.50. And the p-value to 3 decimal places is 0.006. Now, .006 is less than 0.05. Therefore, we would reject the null hypothesis. Those taking IDEL did, in other words, since we rejected the null hypothesis, we now have to go with the alternative hypothesis, which was saying that those taking IDEL did have a significantly higher rate of survival than those taking the placebo. Can the researchers conclude that IDEL causes a better result than the placebo? Definitely, yes. And the actual reason is that the study was double-blinded and uses random assignment. Okay, it met the conditions for the sample, so we don't have to worry too much about it. All right, now we're getting into where we actually have to put numbers into the StatCrunch program or the calculator. As usual, I'm going to show you how to do this, the StatCrunch and the calculator, and then going forward, you can pick your method. Okay. A vaccine to prevent a severe virus was given to children within the first year of life as part of a drug study. The study reported that of 3,213 children randomly assigned the vaccine, 71% got the virus, and out of 1,674 randomly assigned placebo, 51 got the virus. A. Find a sample of children who caught the virus in each group. Is the sample percentage lower for the vaccine group as the investigators hope? So let's see for the vaccine group, it is 71 over 3,213. Okay, put that into your calculator. You want it as a percentage, so times 100, and that comes out to be 2.21%, 2 decimal places. Then the placebo, 51 out of 1,674 times 100 per percent is equal to 3.05. So clearly, for the vaccine group, the sample percentage is lower. Yes, it is 2.21 for the vaccine group versus the placebo group of 3.05. Find the z-test statistic for this test. Okay, so this is where we go to our StatCrunch program. Let's open up StatCrunch. Okay, sign into your StatCrunch, and you want to do stat, proportion stats, proportion stat, to sample. Oop, this is acting really, really strange. Proportion stats, to sample, with summary. Okay, so now we're going to type in the two proportions that we have. So go ahead and type in your proportions. The first one was what? 71 out of the total number was 3,213. That's for the vaccine. And then for the placebo, it was 51 out of 1,674. Numbers look good? Yeah. I close this. Then you're hypothesizing that one is equal and hold on a second. What are we saying here? Okay, lower than. So we're going to take P1 lower than, P2 lower than. We already determined that, right? And compute it. And you get this nice little printout here. So I'm going to go ahead and copy this. Oh wait, I have to. I'm sorry. I have to do something else here to get the copy. Let's use the old snipping tool. Okay, here we go. And put this into our notes. Okay, we're going to go ahead and run this over to our notes. right there. I want to drag this over just a little bit so it's all right. All right, now on this, I'm going to show you how to use the calculator to do this in a second. Okay, but on this, we can observe that we see the z statistic as negative 1.7. Hold on, 1.7 to 2 decimal places, negative 1.78. Why is this on here? Okay, so we're going back here, and then the p-value, the 3 decimal places, is 0.038, correct? 0.038 to 3 decimal places, 0.038. Okay, now let's also do this with the TI-84 calculator. Okay, I want to make sure that we know how to do this with the TI-84 calculator as well. So open up your calculator, and I'm going to walk you through the steps of how to do this with the calculator. Here we go. All right, so we're going to press the Stat button, scroll over to Test, and select two proportion z-test, number 6. And type in for the vaccine 713213. And then for the second sample, the placebo 511674. We already have less than highlighted there, so we don't need to do anything, and simply calculate. And your results are the same, right? Should be the same. I'm going to copy it, paste it over, and compare it. So here we can see the score is the same, and then the p-value is also the same, 0.038, also the same. So we're good to go, yes? We're good to go. Either way we do this. Now, conclusion. So now we're going to compare our p-value to the significance level that we were given. Okay, the significance level is 0.038. So 0.038 is less than 0.05. So we must reject the null hypothesis. Okay, so our answer choices are either B or C. In other words, there is sufficient evidence to conclude. We're rejecting the null hypothesis. We're saying the null hypothesis is not true. So we are, in effect, going with the alternative hypothesis. The alternative hypothesis was that there is sufficient evidence to conclude that the vaccine is effective in reducing the chance of catching the virus at the significant level of 0.05. Okay, now, FYI, if you wanted to check conditions, this is given here. This is not part of the condition. This, if you wanted to go through the whole testing the condition to see if it's more than 10, you can use that process. Add the two, pull the two proportions, get the p-value, then p times n1 and p times n2 should be the same numbers. Yep. All right. All right, moving right along. A study used nicotine gum to help people quit smoking. The study was a placebo-controlled, randomized, double-blinded. Each participant was interviewed for 28 days, and the successes were defined as being abstinent from cigarettes for 28 days. The results showed, first results, 189 out of 1608. This is for the group using the nicotine gum times 100. Calculator. Hold on, I have to. Actually, this is not calculator. We don't multiply this by one. I'm sorry, it is calculator, but we do not multiply this by 100 because they want the answer to 4 decimal places. So calculate and then take it to 4 decimal places, which is 0.1175. And then moving along, 81 out of 1658 used the placebo, so 81 out of 1658. Calculator again, 4 decimal places, 0.0489. I'm using my calculator to get these numbers. Okay. So clearly the proportion of people using the nicotine gum that stopped smoking was greater than those using the placebo. Okay. 11.1175 is greater than 0.0489. This shows that the nicotine gum was helpful compared to the placebo, which is what the researchers expected. Okay. Now we have to go ahead and compute the Z statistic. Find the test statistics for P1 minus P2, where P1 is the proportion of the sample, and then proportion of the sample of people using the nicotine gum, and P2 is the proportion of the sample using the placebo. Okay. So we're going to go to StatCrunch with this. Let me write my numbers down so I don't forget them. 189 over 1608 and 81 over 1658. Okay, and we're going to use StatCrunch. StatCrunch is faster and easier to use than the calculator, but it's up to you guys. So I'm going to go through the process again for those who might have not been following some proportion stats to sample with summary, and type in my values into this table. So I have numbers 189, 1608, 81, and 1658. Equal to and less than in this case. Okay. Compute. Snip. Put into our notes. And let's just drag it over a little bit here so we can see what's. All right, so the Z statistic from this computation to how many decimal places? 2 decimal places is 7.13. 7.13. So I guess that's all they're asking here. Yeah. All right, let's move on. And I'm just doing more examples here. They're exactly the same type of problem. A study reported that the results of the randomized trial of a whole body hypothermia cooling for neonatal hypoxic something, I don't even know what this problem are, brain problems in babies due to the lack of oxygen. 30 of the 90 infants assigned to the hypothermia died, and 44 out of the 99 assigned to the control group died. So uh, 30 out of 90 times 100, the two decimal places is equal to 33.33. Let's write it on the side here. And 44 out of 99 is equal to 44.44. Okay, they're taking percentages here, so multiply by. So the death rate was greater for babies in which group? In the control group, yeah, in the control group. And the control group had a higher percentage. All right, so now we're going to go into the hypothesis testing part of it. Test the hypothesis that the death rate was less than for those treated in hypothermia. So they're actually telling us what to do here. P1 is equal to P2 and P1 is less than P2. They've already given us less than here. And note the significance level. It's not 0.05, it's 0.1. Okay, so it's a higher significance level. So we're going to go ahead and put this into StatCrunch, these numbers. Let's get our numbers here. We've got 30 over 90 and 44 over 99. All right, let's go ahead and hit the StatCrunch program. And at this time, I'm just going to go ahead and edit the numbers, make it faster. Okay, so 30, 90, 44, 99. Everything else is set up 0 and less than. Right, the less than symbol is there already. So we go ahead and compute. And we grab this picture, put it into the notes. And use it to draw, interpret our results. Yes, so let's go ahead. I'm going to paste this here and then drag it in. All right, that's good. So the Z stat to two decimal places is negative 1.56. Okay, that's right there. The p-value is to three decimal places 0.059. Okay, now 0.059 is still less than 0.10. Okay, because they changed that significance level to 0.10. Okay, remember that. It would have been greater than 0.05, but it's less than 0.10. So we still reject the null hypothesis, and we go with the alternative hypothesis. The death rates for baby with hypothermia was less, treated with hypothermia was less than the death rate for the control group. All right, question 11. And you can see the pattern in these problems, yeah? Researchers study a report in which 415 domestic violence defendants were randomly assigned to counseling and probation, the experimental group, or just probation. The control group, out of 236 people in the counseling group, 52 were arrested within 12 months. So 52 out of 236 times 100. Out of 179 people assigned at probation, 41 were arrested within 12 months. Determine whether counseling lowered the arrest rate. Use a significance of 0.01. This is a really small significance level. Okay, now that's 1% significance. Now, calculator would give this as 22.03 to 2 decimal places in 22.91 to 2 decimal places. So the arrest rate was greater for the, this is close, isn't it? Was greater for the probation group. Yeah, probation group. Let P1 equal to PC be the population arrest rate for people receiving counseling, and P2 equal to P2 be the population rate, arrest rate for people not receiving counseling. Okay, so the null hypothesis would be that PC is receiving counseling versus probation, right? And the alternative hypothesis was people receiving counseling was less than, do I have, yeah, less than those that received counseling. Yeah, so those receiving probation were less than those receiving counseling. Be careful here, okay? We head straight to the StatCrunch program and put these numbers in to get a Z statistic. Let's go to StatCrunch. So I'm going to just do this one from scratch. Stat, proportion stat to sample with summary. Type in my numbers here. So the first one is 52 out of 236. And the second one is 41 out of 179. Let's check our parameters equal, and this has to be less than. Compute. And we copy this over to our notes. This is our results here. Drag this onto the page. All right, here we go. So this is our printout. The Z stat is right there, negative to 2 decimal places, so it's negative 0.21, and the p-value to 3 decimal places is 0.417. Okay, so remember this significance level is 0.01. So let's see. 0.417 is greater than 0.01. So we do not reject the null hypothesis. Do not reject. Counseling has not been shown to lower the arrest rate. Okay? The null hypothesis is that counseling has lowered the arrest rate, is less than for people receiving counseling is less than people who are out on probation. Did I use PP here? This is PP, not PP. PP. I'm sorry, PP. My bad. PP. Yeah. People who are taking counseling is less than PP. So because we did not reject the null hypothesis, we cannot conclude that the alternative hypothesis is acceptable. Okay? It has not shown that, or evidence has not shown that. All right, final problem. In a study, people were observed for about 10 seconds in public, such as malls and restaurants, to determine whether they smiled during randomly chosen 10-second intervals. Find and compare the sample percentages of who was smiling and not smiling. So, smiling percentage of men who were smiling in the sample. So the sample total for men, let's add these up. We need to go ahead and add them up. 3,161 plus 3,549, 6710. So the sample for men who were smiling was 3,161 over 6710. Times 100, which according to my calculator is approximately 47.11%. 47.11%. And then the percentage of women who were smiling, so the woman total column is 4028 plus 4004, which is 8032. So a woman who was smiling was 4028 over 8032 times 100. Put that in the calculator. 4028 plus 8032 divided, I added it, 4028 divided by 8032 is approximately 50.15%. So the sample for people who was greater for the women, okay? Women smile more. Now treat this as if it were a random sample. So they're telling us that the condition is met, and test whether there are significant proportions of women, men and women, who smile significance level 0.05. In other words, we're testing to see smile or don't smile for women. okay? And for men and women, sorry. So we're looking for equal and not equal. Right there, equal and not equal. Okay? Remember, P1 for the null is always going to be equal, and in this case, we're looking for smile and not smile, nothing less than or greater than, just simply smile or not smile. So we want to put these numbers into our StatCrunch program, 3161 over 6710 and 4028 over 8032. Okay, we're going to put them in because we need to get the z-stats and draw and interpret the results. So let's head for StatCrunch. Let's do this from scratch again. It's easier to just go ahead and type in. So stat, proportion, stats, do sample with summary. And we're going to type in all of the values that we have. So this is 3161. 6710. Then second case, 4028. 8032. We have equal to each other and not equal to each other already selected. Compute. Copy and paste this. Bring it in here. Drag it in. All right, there we go. So the z value to 2 decimal places, 3.68 negative. Okay, that's that number there. And the p-value to 3 decimal places, this one, is 0.000, because we can't round up that third number. Okay. Compared to 0.05, so 0.000 is clearly less than 0.05. We have to reject the null hypothesis. And there's two answers that deal with reject. Let's see the explanations. One says there is not a significant difference in the rate of smiling for men. The other one says there is a significant difference. And so because we're rejecting the null hypothesis, we're saying that there is a significant difference in the rate of smiling for men and women. Okay? Because we're going along with the alternative hypothesis, since we're rejecting the null hypothesis that they're equal. The null hypothesis is saying that the women and men smile about the same. This is kind of common sense here. When the proportions already show that women are smiling more, so there is a significance difference. Finally, explain the size of the p-value compared to the difference in the sample percentage. So clearly the p-value is very small. Okay, the p-value is 0.000, and we're looking at possible answers B and D. And now let's look at the explanation. The first one says the p-value is small compared to the difference in the sample percentage. The difference in the sample percentage is significant because the sample size is clearly large. Okay, good. I like this explanation because this one saying is not significant even though the sample size is large. Remember what we said about large sample sizes, that they make the results, the p-value, even more significant. So long lesson, but we've got through it. These are all 12 of the problems. Let's go ahead and finish this up.